This video will be discussing about the virtual memory. As you know that design of the memory is influenced by three factors: speed, size, and cost. To increase the speed of the memory, accessing speed of the main memory, we use the cache memory for the same. A small cache memory is introduced between the processor and the main memory. However, to increase the apparent size of the main memory, a technique that is being used is called the virtual memory. For cache memory was not just a technique. Cache memory is a physical small memory is placed. Virtual memory is a technique, and it is usually being provided by an operating system. So recall that an important challenge in the design of computer system is to provide a large, fast memory system at an affordable cost. So we require what? Large, fast with an affordable cost. To make it fast, we have used the cache memory. Now we have emphasis on this large, for which we will go for the virtual memory. Architectural solution to increase the effective speed and size of the main memory system. Cache memories are developed to increase the effective speed of the memory. Virtual memory is an architectural solution to increase the effective size of the main memory system. So main objective of the virtual memory is to increase the effective size of the main memory system. You know that addressable memory space depends on the number of address bits in a computer. If the processor generates 5 bits, that means we have 2 to the power 5 number of locations. If my system issues, processor issues 32-bit address, that means 2 to the power 32, that is 4 GB. My main memory is of 4 GB. So according to the addressability of the processor, the main memory is determined. So physical main memory in a computer is generally not as large as the entire possible addressable space. So it cannot be more than what the processor generates an address. So physical memory typically ranges from few hundred megabytes to 1 GB, and nowadays we may have some 4 GB, 8 GB, 16 GB, or 32 GB of memory. So large programs cannot fit completely into the main memory. Suppose we have our system with 4 GB of RAM. We want to execute a program of 5 GB. So now, as my computer system has maximum size of 4 GB of RAM, you will be thinking that we cannot execute a program of 5 GB. But here it says the program will be stored in the secondary storage. A part of the program may be loaded into the main memory. We'll go on executing that part of the program. When the rest part of the program is required, a part of the program which is already there in the memory is moved to the secondary device, and the requested part is brought into the main memory. This is called swap in and swap out. Taking the information from the memory to the secondary device is called the swap out or roll out. Taking the data from the memory to the from the disk to the memory is called the swap in or roll in. When a new piece of program is brought, of a program is to be transferred to the main memory, and the main memory is full, then some other piece in the main memory must be replaced. And that was also there in the cache memory. When the cache memory becomes full, we replace it. Similarly, in the main memory, when it becomes full, a part is also replaced with this data that is there in the secondary memory. So operating system automatically transfers data between main memory and secondary storage. So application programmer need not be concerned with this transfer. So operating system handles all this. So the technique that automatically move program and data between the main memory and secondary storage when they are required for execution is called virtual memory technique. So look over here, it's a virtual memory technique. So it's a virtual memory is actually a technique. It is not any hardware over here. So programs and processors reference and instructional data independent of the size of the main memory. Now, if my operating system allows virtual memory concept, so the processor can generate an address which is independent of the size of the main memory. So processor can generate an address beyond the main memory size. If my main memory is of 4 GB, with maybe of 32 bit, it can generate an address more than this 32 bits. The processor issues binary address of instruction and data. The address generated by the processor is called logical address or virtual address. Address generated by the processor is known as logical address or virtual address. Actual address in the main memory is called the physical address. So there is as the data is actually found in the memory, so this virtual address or logical address is need to be transferred to the physical address. Who converts this? There is a unit called memory management unit, which is responsible for converting this logical address or virtual address to a physical address. So processor generates the virtual address. It goes to the memory management unit. It converts this virtual address to physical. How it will be convert? That address translation part we'll read. We'll read later. Now virtual address is given to this memory management unit, which converts into physical address. If it is a data, it can be directly given to the cache. So now this physical address is given. We'll search whether it is present in the cache or not. If it is found in the cache, it is good. If it is not found, then it is searched in the main memory. If it is not found in the main memory, then it will be read from the disk storage. Generally, the reading data from the disk storage in form of DMA transfer. DMA stands for direct memory access. Direct memory access. This is a transfer technique, IO input-output transfer technique. So here, the memory management unit is responsible for converting virtual address to physical address. But now question is how this address translation takes place. Here it says the program is divided into fixed size blocks. The program may be now more than the size of the main memory. The program is divided into fixed size blocks called pages. The main memory is divided into some fixed size blocks called frames. So try to understand, we have main memory is divided into fixed size blocks. The program is also divided into fixed size blocks. The blocks that are being divided for the program is known as pages. The blocks that are divided in the main memory are called frames. The size of the page is equal to the size of the frames. So I can take a page, put it somewhere in the one frame, and one frame may be replaced with one of the page. So the page size equals to frame size. However, number of pages may not be equal to the number of frames because the program size may be greater than the main memory size. So number of pages may not be equal to the number of frames. So what is a page? Page is nothing but a fixed length, fixed number of blocks. A page consists of block of words that occupy contiguous location in the main memory. So what is a page? Page may consist of a number of words. A block having number of words. Page is a basic unit of information that is transferred between secondary storage and main memory. So if I want to transfer some information, I will transfer a page actually. So page, what is a page? Page has a number of words. So size of page commonly ranges from 2K to 16K. This actually depends on the operating system. The page size should not be too small because if I have smaller number of pages, then many times I have to access from the secondary storage. Write operation, as you know, is more costly. So there, as compared to read operation, so it will take a lot of time. And the page size should not be too large. If it is too large, what will happen? A substantial portion of the page may be unused. The concept of virtual memory is similar to the concept of the cache memory that you have read. So what is that in cache we have read? Introduced to bridge the speed gap between the processor and the main memory. Here you have bridged the speed gap between the main memory and the secondary memory. So we have kept the cache memory between the processor and main memory. Here the virtual memory actually acts between the main memory and secondary memory. Cache memory is implemented through an hardware, where the virtual memory is a part of software and usually by the operating system. So the virtual or the logical address generated by a processor is interpreted as a virtual page number and as an offset. So address generated by the processor has two parts. One is called page number, another is called the offset. The high order bits are called page numbers, low order bits are called offset or address. The information about the main memory location of each page is kept in a table called the page map table. So we can see this through a diagram. Here, the virtual address generated by the processor is called, this is the address generated by the processor, which has two parts, virtual page number and offset. The page number says in which page contains the data. This offset says inside that page in which location we'll get it. Now our objective is to convert this virtual address to physical address. What is physical address? The actual address in the memory. Now we have a table called page map table or page table or page map table. This page map table contains what? The frame number for each of the pages. Suppose page 5 is stored, then what is the where it is stored in the main memory? Suppose page 5 is stored in frame number 7. So fifth entry, 1, 2, 3, 4, fifth entry will contain 7. That means page number 5 is in frame number 7. If page number, suppose page number 12 is stored in frame number 1. So 12th entry over here, 12th page number, and what is the frame number over here? 1. So how many entries will be there in the page table? The number of pages in the program. And for each page, if it is stored in the memory, in which frame it is being stored. So this maps actually a page number to a corresponding frame number in the memory. And there are some control bits. So these are the page frame actually. These are the page frames, and these are some control bits over here. So what are these? These are the frame numbers of a corresponding page. So what is the page number need not to be stored because these are already in order. First entry for page number 1, second one for page number 2, page number 3, up to the number of pages. Page number 1 is if the page number 1 is there, it is in which frame. If page number 2 is there, in which frame number. This is the page frame, and these are the control bits that are being used. What are the control bits? Control bits are different access bits or for security reasons also, like read, write, execute, modified bit, valid bit. Those are being as others, which are the set of control bits. So address generated by the processor has two parts, page number and offset. We have a table called page map table, which has two fields over here. One is frame number, and is a control bits. These are according to the page numbers. These are being stored according to the page numbers. Now, the starting address of this page table is being stored in a register called page table base register. Starting address is stored. So if I have fifth entry, suppose this address is 1000, I want the fifth entry. So that means 1000 plus 5 I have to go. So this page number, which is being generated by the processor, is added with this page table base register content, and we'll get the corresponding entry over here. Actually, what happens? If it is fifth entry, it is 5 into size of each one. Like we access an element in an array. If I want to access the fifth location and the base address is known, then base address plus index into size of each entry. Similarly, this is the base address. If the size of each entry we know, that into the index gives you the address of in the page, from which we can get the corresponding frame number. If the page number we got and the index of the page entry we got, then we can get the corresponding frame number. This is the frame. As we know that the page size and frame size are same, the way that data or the words are stored in page In the similar way, it is also stored in frame. So the offset that is being used over here with the page number, the same offset can also be used from the frame. So I can just concatenate this offset to get the physical address. This is the way the virtual address is converted to the physical address. So that is being explained over here. So we have the page table entry for a page also includes what? Some control bits we have already discussed. So one bit is for valid bit, one for maybe read, write, different purposes it may be kept. Now question is that where to keep this page table, because this information, the page map table that we have discussed, this page map table or page table has to be kept somewhere. So ideally it should be kept inside the processor. If it is there inside the processor can easily get it, or faster it can be accessed from the processor itself. But however, there are limited number of registers in a processor. So this large PMT may not be kept inside the processor. So what do we do? So instead of keeping there inside the processor, we keep it in the main memory. However, a small part of that which is very frequently used can be kept inside the processor. So here, the page table is used by the memory management unit for every read and write operation. So it is this where this MMU is actually, in many cases it is part of the processor, and page table is quite large. So MMU is implemented as a part of the processor chip. So it is impossible to include the complete page table on the chip. So it is usually being kept in the main memory. However, what we can do, a copy of a small portion of the page table can be accommodated within the MMU. So which small portion? The portion consists of page table entries that correspond to the most recently accessed. So many of the pages which are very frequently being accessed, that portion can be stored inside the MMU. So if you keep in the MMU, what happens is that small cache is known as translation looped aside buffer, or TLB. So TLB is a small cache which stores what? Which stores the frequently accessed page information. So unlike PMT, it doesn't only hold the frame number, it stores the page number, frame number, and the control bits. So like in our cache memory, we hold recently accessed blocks. From here also TLB stores the recently accessed pages. So what it stores? It stores the page number, frame number, and the control bits. So what now the processor will do what? This is the address generated by the processor which has page number and offset. So before searching in the PMT, first it searches in the TLB. What the TLB contains? TLB contains the page number and the corresponding frame number with the control bits. So there are limited number of entries in the TLB. So the search is made to find whether it is present in the TLB or not. This search is a parallel search. This search is called the associative search. So therefore it is called the associative map TLB. So all locations search in parallel. So either it is found, if it is it's called a hit, it may not be found in TLB, we say a TLB miss. If it is found in the TLB, the corresponding frame number can be obtained, to which the offset can be added to get the physical memory. If it is not found, what we'll do? If it is not found, it's not found in the TLB, then we'll go to the PMT. The PMT, as we know, to go to the PMT, it will get the corresponding entry over here by adding to the base register. The corresponding frame number will get. Frame number can be added with the offset so that the physical address can be obtained. This is the way the address translation can be done. So how to keep the entries of the TLB coherent with the content of the page table in the main memory. Now, if you have any change in the page map table, the same has to be reflected in the TLB as well, because TLB contains a part of this our page table. So therefore, operating system may change the content of the page table in the main memory, simultaneously also invalidate the corresponding entries in the TLB. So for that, a control bit may be provided. There are some more concepts associated with this virtual memory concept. One is called the page fault. If the reference page is not found in the main memory, a page fault is said to occur. We are searching for a page, and if it is not found in the main memory, we say it's a page fault. So if a page fault occurs, what do? We'll bring it from the secondary device to the main memory. The miss penalty that we have in the cache memory, similarly we have page fault over here. In cache memory, if you have miss penalty, we bring the data from the memory to cache. So if a page fault occurs, we bring the data information from the secondary memory to the main memory. The requirement is there should be less page fault. There is another concept associated with this virtual memory is called the demand paging. The demand paging says a page will not be loaded to the main memory unless and until it is being demanded. That means unless the processor has not requested for a particular page, that will not be loaded to the main memory. So in result, what will happen when the program starts executing? First, the information that is being requested will definitely not be found in the memory initially. So that is a compulsory page fault that will definitely occur. Then it will be brought from the disk to the main memory. So if you are using demand paging, some compulsory page fault will definitely occur. So there is another concept over here is called the pre-paging. The pre-paging says even if it is not being demanded by the processor, the information or some blocks can be transferred from a page. Some of the pages can be transferred from the secondary device to the memory, assuming that these pages may be in use. So if those pages are in use, then we may not suffer from page faults. There is another concept called the thrashing. A high page fault is called as thrashing. That means if I have 4 GB of RAM, I want to execute a program of 8 GB or more than that. Now what will happen? My operating system allows for the virtual memory. But what will happen? Many times the page will not be found and it will be brought from the main memory, from the disk to the main memory. And from main memory, a page may be swapped to the disk, and the process will continue for longer time. But frequently it will happen. So the processor will spend most of its time is in page in and page out, or roll in and roll out operation rather than actual execution, because the processor has to do this swap in and swap out operation. So processor spends most of its time in swap in and swap out operation rather than actual execution. This is known as thrashing. So high in short, we can say a high page fault results in thrashing. So therefore, thrashing is not at all desirable. So this is the concept for the virtual memory.